So I'm just going to go briefly then over our approach to 4-pi trajectory optimization, and others have taken different approaches. If we imagine a gantry rotating, in this case, around a PTV and a brainstem, there are certain angles where we have very little overlap between these two structures and others where we have a lot of overlap. And so we can actually plot the overlap, as I've done here in the bottom right plot. And then if we do that actually for every possible couch angle, we can come up with an overlap map, a composite overlap map. So the darker blue areas show areas and couch gantry combinations that involve very little overlap. And then we have higher cost in terms of overlap. We can do this for all organs at risk, and if we want to, we can weight those layers, for example, with radiobiological factors or importance factors, and we come up with a composite. So this is kind of interesting because we can use it quite simply. We could use a fixed couch delivery and just use this map for intelligent selection of those fixed couch angles. Or maybe in the future, we can do something like this, where we're actually navigating dynamically with synchronized couch and gantry rotation, the minimum in this overlap map. So I'm putting up this slide just to make the point that if we do this for 20 randomly selected cranial radiosurgery patients, they all look quite different from each other. And that makes sense because we treat indications throughout the cranium. And some patients would benefit from a gantry rotation, leaving the couch fixed. Others might benefit from a couch rotation, leaving the gantry fixed, and others a combination thereof. So this is kind of the teaching part of this talk. When you use cranial elements, it looks like a very slick and shiny black box sometimes. It's very turnkey and automated, as Daphne was describing. And I'm going to try to explain it to you in 3 easy steps, okay? So the first is in terms of arc optimization, the planner specifies a protocol, for example here, single fraction of 15 gray. And for that protocol, there are 3 possible template setups. And after this is done, those are fed to an objective function that figures out automatically the best appropriate template setup. Now, how does that objective function work? It actually considers a couple of things. First of all, it's the PTV-OAR overlap, as we worked on in our research. It actually only considers organs at risk on the upstream side, not the distal side of the PTV. And the second factor is the total radiological depth. So it will examine all the points on arcs for different couch angles and actually evaluate that. So we were evaluating cranial elements with this arc and setup optimization for the first time. So as an initial step, we fed it right-handed, centered, or left-sided PTVs and just checked whether it did sensible things. And you know, this is kind of interesting. The system was doing pretty much exactly what I would do as a human planner in terms of the bias, in terms of laterality. So the step 2 here is if we have a template couch angle specified in our template, shown as the blue couch angle here in this hemisphere, the system will actually generate a whole family of candidate couch angles. And in doing so, it looks at whether the gantry angle is a full arc or a partial arc. And if it is an arc over 180 degrees, it does something very smart and actually only generates candidate angles towards safer angles. That is approaching coplanar. And that's important because the system automatically then minimizes collision or the potential of collision between couch and gantry or gantry and patient. So let's build onto this objective function now. We actually have a third term. You might have a planner who says, I really like the templates that I supply, and I trust them and I know them. And I'm going to let the system adjust those couch angles, but only by a little bit. And so here we are introducing a third penalty factor, which penalizes deviation from the template. Or conversely, we could have a treatment planner that says, I trust the system and I want to allow full latitude in selection of couch angles. So now we have optimized couch angles and move on to step 3. It could be that the gantry arc span at each of those couch angles is not optimal from the template. And I thought I would try to explain this to you because it's really kind of interesting. And this is some of the under-the-hood innovation in cranial elements. So we're going to consider a gantry arc. We're going to calculate lap at each control point. We're actually going to determine the global average, and from that average determine a threshold. And then we're going to start to trim the arc, or the ends of the arcs, where we exceed that threshold. And so, and in doing that, we are going to specify a minimum allowable gantry angle range. So let's do a little example here. Round 1, we calculate the global average. We have a threshold of 1.7. We examine from this end, we've ran into a 5, and so we're going to trim the arc. We'll do the same thing from the other. Immediately we run into a 2. We move on to round 2, recalculate that threshold. We trim that 6. And from the other end, we don't actually meet a value that exceeds our threshold without shortening the arc below our minimum. And at the end of this process, we actually have a final trimmed arc. So let's build on to our objective function. Similar to penalizing changes in couch angles, we can also penalize changes in gantry start-stop angles. And so the user can allow a lot of latitude here or restrict it. So we were really interested to see how this worked, and so we started off by taking 10 vestibular schwannoma cases. The status quo in my center was rapid arc, the VMAT approach. We actually considered 4 different plan types, elements, but turning 4-pi off as a baseline. Elements where we actually enabled 4-pi but omitted the brainstem from the 4-pi optimization. And the reasoning there was we thought, well, the brainstem is actually going to be in almost all of the beams I've used here, and we thought it might be a little bit too demanding. And the 4th case was actually allowing 4-pi to work with all the organs at risk. We started off with a baseline template here. I wanted to use a symmetric template like this because I was really curious to see what the system would do with it. And we, for the vestibular schwannoma, we ensured 99% volume coverage at the 90%. We used non-overlapping PRVs. And then we compared in terms of PTV metrics, in terms of dose homogeneity and OAR sparing and MU efficiency. We did similar for 10 pituitary adenoma cases. We just didn't do the case where we omitted the brainstem. So some results. We see a comparison here between rapid arc and the 4 cases. The little chevron at the bottom indicates where a P was less than 0.05 based on a Wilcoxon rank test. We see a little bit better dose homogeneity with elements. But I do want to emphasize that the point here wasn't really a rigorous comparison with rapid arc. It's actually very difficult to compare 2 planning systems because of the many variables involved and different ways of specifying dose volume objectives. If we move to the brainstem, we can see a trend here. So when we move to elements but with no 4-pi, we saw slightly improved mean dose. When we actually turned on 4-pi, but with no brainstem, we actually saw a slight improvement. And I think that was serendipitous. The arcs were being optimized to spare optic structures, and that had an effect on the brainstem. And then when we allowed the 4-pi algorithm to actually consider the brainstem as well, we saw an additional improvement. But the maximum dose really didn't change between these different elements plans, and that's really because all of these target volumes were abutting the brainstem. And it's really very difficult to lower that through arc optimization. So just an example, the baseline is on the left without 4-pi, and it's really interesting to see what the system has done to achieve this. And again, it did something a little bit like what I might do as a human planner. You can see it first of all biased the arcs in terms of adjusting the couch angles, And it moved those arcs to minimize the intersection of the arcs with the brainstem. How about optic structures? We saw a statistically significant improvement in max dose to eyes and lens as soon as we turned on the 4-pi algorithm. You can see, though, when we actually allow all organs at risk, including the brainstem, to be considered, things become a little bit worse, and that is because the brainstem sparing is actually competing with the optic structure sparing. And we see actually similar behavior for the optic chiasm and optic nerves. And so here's another example. With 4-pi on the right, you can see that the system actually shortened these arcs as well as changing the table angles to lift them off of the eyes and the optic nerves. Inverse Paddock index, this 4-pi algorithm isn't by design meant to improve dose conformity. We did see a bit of an improvement going from rapid arc to 4-pi. The gradient index is quite interesting to me. So this is the volume of the 50% isodose divided by the volume of the PTV. I was interested to know whether by skewing these arc arrangements, we were actually enlarging the 50% volume due to potential arc overlap. And it doesn't appear that the system is. I think the improved conformity can be explained quite simply, and Dr. Levin referred to this. Elements in the background is actually placing a couple of tuning structures around the PTV to try to ensure conformity in a very compact dose distribution. Monitor units. So we saw a reduction of total monitor units as we moved from rapid arc to 4-pi. Typically, these cases involve a lot of modulation in rapid arc. And then we saw a slight decrease actually when we enabled the 4-pi method. The results, I'll go through these fairly quickly for pituitary, mainly because we see similar trends. So we see reduction of mean dose for brainstem when we enable 4-pi, maximum dose due to the proximity and the fact that it was abutting in most cases was not changed. Eyes and lenses, we saw an improvement, first of all, moving to elements, and then again as we enabled 4-pi. Here I just wanted to show this example for a central lesion, this pituitary adenoma. What the system's actually doing is tipping these arcs slightly towards the vertex, which is minimizing or reducing the intersection with the optic nerves. Conformity improved slightly again as we moved to elements, but not further when we enabled 4-pi, and gradient index was improved a little bit by going to elements. Monitor units for pituitary adenoma cases, I think we really pushed the optimizer quite a bit. It was very demanding in elements, so we saw actually an increase of monitor units. But the interesting thing to me here is when we enabled 4-pi, we see quite a large reduction in the monitor units required. And that is because as soon as you are minimizing naturally the overlap with organs at risk, less modulation is actually required to actually spare them. And so this is the kind of result we saw here. Without 4-pi on the left, we have a lot of intersection here with an orbit and the brainstem, and as soon as we start to develop smart trajectories, we have much more open and simpler apertures, and it becomes more MU efficient. So just about 1 minute on future directions. I'm now going back to the research world. So we would really like to get to the point where we are delivering truly dynamic trajectories. That example that I referred to at the beginning with simultaneous couch and gantry rotation. We can do this in developer mode right now on a TrueBeam system, but not clinically. But one thing that we can do clinically is approximate that smoothly dynamic delivery with a number of arc segments. And so if you can imagine a smooth trajectory moving through that overlap map, we can approximate that by a number of fixed couch deliveries. And we wanted to know how does the resolution of that approximation affect the result? So you can see in the pink lines, we have a very coarse approximation with 3 couch angles, and we move all the way up to 36 separate arcs, which in concept could be planned automatically and delivered automatically. And what we see actually is that as we improve the resolution of that approximation, we start to improve the dose received by 10% of the brainstem volume. All of those results are a little bit better than what I'm producing now with elements. So I think there are more steps here and more innovation to be done. We also see an improvement as we increase that resolution of the dynamic arc with conformity. But some of those cases actually rival what we're doing now in elements. So I'm going to summarize very briefly. It's really great to have been working on a project and to actually see some of that innovation in around 15 months reach the product and start to reach patients. Elements, I think one of the benefits will be the automation. So, and encouraging the uniformity of plan quality through automation. So new arcs are generated based on a user-supplied template. So that's actually a very pragmatic approach. It starts with something that is comfortable to the treatment planner and modifies it from there. It modifies by optimizing first couch angles and then gantry arc span. And in many of the cases, the dosimetry was improved for brainstem and optic structures. And by simplifying arcs in terms of the intersection with organs at risk, it becomes more efficient. I want to thank a very hardworking grad student in the medical physics graduate program, Lee McDonald, and my physicist colleagues, Dr. Syme, Thomas, and Parsons. Thank you.